Let's start this session now, and I have the honor to present Heinz Kabutz, it's a Java champion, and I think this talk will be really interesting, but we have to keep it in 40 minutes, 45 minutes.
Okay.
Okay?
Well, let's get started. Thank you for coming. So we want to look at how we can improve our CPU utilization when we use something like fork join. And here's a graph that's sort of a regular without ManagedBlocker. I'm going to talk about ManagedBlocker. I'll tell you what it is in a moment. And this is without ManagedBlocker, and this is with ManagedBlocker. So it's the same basic code, but in the one case, I'm using ManagedBlocker, that's the second one. In the first case, I'm not using ManagedBlocker. And this is quite a large calculation, so you can see it takes quite a few seconds to run through, several minutes actually. And at the end, with the ManagedBlocker, I'm about 8% faster. So if you're trying to squeeze out the last bit of performance, it can give you an upper hand here. The difference is at the beginning. So if you look at the beginning, you'll notice that we've got, there's quite a bit of, there's not that much black at the beginning of the cores. Now this is on my laptop. My laptop has got 4 cores, and it's got hyper-threading. So it shows at 8 cores, but it's not really 8 cores. It's really just 4 cores with hyper-threading. Hyper-threading gives you an advantage, but not in number crunching like what we're doing over here. If you compare to the previous diagram, over here you can see there's a lot more black at the beginning. So there's quite a bit of black. And the black here is problematic because the black means that we are not utilizing the available hardware. Once everything starts up, then we're doing okay. But in the beginning, we could utilize it better. And as I showed you, this gives me about an 8% improvement, which might be useful to you. So we're going to look at a number that's always difficult to calculate, called the Fibonacci series. And this was done by a guy called Leonardo of Pisa, and his father was called Nacci, so he's called Fibonacci. And it's a very commonly known sequence. F of 0 is 0, f of 1 is 1, f of n is the 2 previous numbers added together. Very simple mathematical equation. And it occurs all over the place. You can see this sort of picture I've got there. That actually is the series in picture diagram. You can see it gets bigger and bigger and bigger and bigger, and it gets bigger very quickly, as you can ask. You can find it with the Australian rabbit population, where it just doubled and doubled and doubled effectively, and kept on increasing in size until they had like billions, I don't know how many, many rabbits, which have fortunately been reduced now. Now, if you pick a naive implementation, this is sort of really bad implementation. It's a terrible example. What we do is we take the mathematical equation, we simply write it as Java. So we're going to say if n is 0 or 1, we return n. Otherwise, we return the previous ones added together. Now, it uses recursion. Recursion in itself isn't bad. The problem here is that we're working out the values over and over again. And the actual complexity, the time complexity, computational time complexity of this is in itself a Fibonacci series. So you end up with very, very bad performance. Okay. Now, if you want to see where this is actually used, I've seen it in a book, right? In a book on performance, where they say, let's say you want to work a Fibonacci 100 with this formula, right? Fibonacci 100 will take you like 1,000,000 years. Fibonacci 1,000, I've tried to estimate it because it's quite a big number. My closest estimation is something around about 10 to the power of 200 years. Years, right? It's a number which is so astronomically large, we can't comprehend that in our little minds, you know? We're not talking about billions and billions of years, we're talking about 10 to the power of 200 years. So, and there's another place where this number, where this function occurs within a class called recursive task in Java, in the JDK. As an example of how we can use fork join, right? And if you use that, you're going to find, my goodness, this is complete rubbish, it doesn't work. Okay. So, another way of doing it is to do iteration, to have an iterative algorithm that simply goes from 0 up to n and just adds the last 2 numbers together. So this is the actual algorithm is linear, which is great. If you want to work out Fibonacci 1 billion and you use longs, you can do that in 1.7 seconds. However, the number overflows round about Fibonacci 70 or round about there. So you're not going to have the correct answer, but you'll get it quickly. So that's great. You can get a fast, wrong answer. Now, we could use big integer instead of long, but the add function is in itself also linear. So you've got a linear add multiplied with a linear function gives you the quadratic time. So it's not going to work. It's just not going to work. So here's a better algorithm. There's one which is even better, which I can't comprehend in my little brain. But this is hard enough. This is Dijkstra's sum of squares. And if it's an odd number, you've got one calculation. So f of an odd number. If it's f of an even number, you have another calculation. And this means that at every step, we are decreasing our number by half. So it's actually logarithmic complexity for the actual algorithm. And then instead of using add, we're using multiply. Now, in older versions of Java, the big integer multiplier was in itself also quadratic. So again, you didn't have much chance with that. But since Java 8, they now have got two additional algorithms. They've got Karatsuba, when the number's not too big, and they use Tum Cook when it's bigger. So bigger numbers use Tum Cook. So, and unfortunately, it's still single-threaded, and we'll fix that in one of the demos. So the first demo is to take this algorithm that you see over here and to implement this as Java. Now, I'll jump over into my IntelliJ, and over here's my Fibonacci. This is the old algorithm, and the only test that will run is the test simple values. If I run that, that should run through and should say everything is good. The Fibonacci 1000 will take, as I said, approximately 10 to the power of 200 years. So we don't really have time. He said 45 minutes, is that right? So that's not going to work. Forget, we're going to even try running that. Now we look at Fibonacci. You can see that this algorithm is terrible. What we're going to do is we're going to code the algorithm that Dijkstra figured out, which is we sort of divide n by half. So it's going to be n plus 1 divided by 2. Then we're going to say big integer f naught equals f of half minus 1. And big integer f1 equals f of half. And then depending on whether n is odd or even, we're going to either do that one with this adding of the squares, or the other one, which is a bit more complicated. Here you can see the two calculations. Let's try that. We're going to say if n, no, we need to say if n percentage 2 is 1, if it's odd. And in this case, Java's clever enough to optimize that to bit masking. Then we're going to say return f of naught dot multiply with f of naught dot add f of 1 dot multiply f of 1. Okay. Else, we're going to say return f of naught. We're going to multiply by that by 2. So here we're going to say we're going to simply shift the value left by 1 bit, dot add f1, and then we multiply all of that with f1 again. And now we can, if you run this again, it should hopefully run through everything. Some of the numbers are still very large. I mean, I'm working out Fibonacci 100 million, and 100 million is an astronomically large number. But you can see that it did Fibonacci 1000 in 5 milliseconds, right? So as always, you're going to, as you normally find, you get far more benefit out of improving your algorithm than you would ever get out of parallelization, right? So if you're going to do stuff in parallel, before you even think about that, see, can you improve the algorithm? Because that's going to be many factors more, right? If you wanted to do this in parallel and you took the sample code out of that one performance book that I'm not going to mention by name, or the recursive task class in Java, which I will mention by name, then it's going to actually tell you, instead of taking 10 to the 200 years, Fibonacci f 1000 will now take 10 to the power of 199 years if you parallelize it. No, that's not true, because that's years, right? So it's going to be, it's ridiculous, right? So for 100 million, we managed to solve that in just under 46 seconds. So we're going to write that down. And this is actually the first demo. So I must just do a quick commit on that. So git commit. And my plan is to do this with every demo, so that in the end you can compare all the differences once I push everything. So this is the first demo, and you can see that we managed to run it in about 46 seconds for 100 million. Now the only thing I'm really caring about here is the 100 million. The other ones are fairly fast, and at this point I don't care about using JMH. JMH is good for many things, but not for doing this presentation. Right? So we're not going to use that. So I'm commenting out all the tests except for the 100 million and the actual sanity check to make sure that my algorithm works. Now, if you run this again, I want to show you something. We're going to open up top and sort by CPU, and you notice that my CPU stays at 100%. Okay, it's right about 100%. Sometimes it goes slightly more, because we also have garbage collection happening, which is going in parallel, but it's generally staying at about 100%. And we can improve that. What we can do is we can use something called fork and join. What that does is I need to work out F1 and F0. So what I could do is I could work out F0 in the background with a forked task. Then I could work out F1. And once I'm done with that, I could join back to I could join the value of F0, and hopefully that would have been done by then. And in this case, I'm just going to use the default common fork join pool. Of course, you could also use your own, but I'm quite happy to just use this one. Is this flickering all the time? I think the cables are rather suspect. Let's do this. So we're going to go, and we're going to, over here, say fork join task, big integer, and it's going to be F0 task equals new recursive task, not fork join pool, fork join task, sorry about that, equals new recursive task, and I'm going to take the code that's here and just move it into my compute function. Then I'm going to fork the task, so I'm going to say fork over here, and after I've worked out F1, I'm going to say F0 task.join. So now I've managed to do a fork and a join. So I'm forking the F0, doing it in a separate thread, maybe not, but I'm making it possible for that to happen, and then I'm running and afterwards joining with that. Now, if you run this, we now, instead of using just one core, I'm using 4 cores. Right? It's an 8-core machine, but it's not really 8 cores, it's 4 real cores. Right? So the speed up I would hope to get is for it to be 4 times faster. That's what I want. Of course, I'm not going to get that, because life's not fair. So let's run it, and it's happily going there, and it's crazily constructing many objects, because it's a big problem we're trying to solve. And once it's done, it comes back, and you can see it's not half, it's not a quarter. It takes longer. I hope I'm doing this right, because it is taking far too long. Maybe it just seems long, because I know I've only got 45 minutes to get through this whole talk. And okay, so this is what I was expecting. We're getting a number of about 24.5 seconds. That's not even half. It's not even half. Now, I'd like to just, whilst I'm just writing this down, I'd like you to think about why it would be not actually using, or not being better, right? So this is my second demo, so I'm going to just say commit -a, git commit -a, demo 2, right? So when you look at it afterwards, you can see all the different things. So if you run this code again, and you open up top next to it, you can see in the beginning, Java's running at like 700%, right? And that's great, that's what we want. But then it drops down to like 200%, and after even longer, it drops down to 100%. So I'm not actually utilizing the hardware that I've got. Any ideas why? Yes, sir. Okay, it's actually a characteristic of recursive decomposition. It's a characteristic you'll see when you're doing a merge sort, or and what's happening is that it's very efficient to break up things into small sections. But then when you bring them back together again, when you're doing the final multiplication of the largest number, you can only do that single-threaded with the current design. So we have managed to improve our performance at the beginning, but not at the end of our call. So what we're going to do, just to improve this a bit, is I'm going to add some timing information into this section down here where I'm doing the actual multiplication. And what I'll do is I'm going to only do it if n is bigger than some number, because system current on millis is also quite expensive to call, so we don't want to do that all the time. So it's going to be, if n is bigger than 1,000, we're going to call system.current time millis. Otherwise, we just set it to 0. And then we're going to say try, and finally, time equals, again, if n is bigger than 1,000, we're going to do system current time millis minus time. Otherwise, we just make it 0. And then if time is bigger than 100, let's make it bigger than 50, then we're going to print out fib n, let's put a bracket there, took, and the time. So you can see how long it took. But not for the very small numbers, only for the bigger numbers. We can see how long it takes. And I think when you see the output, you'll realize two things. All right, you can probably see already a problem if you look at those numbers. Besides the fact that some take longer than others. As the numbers get bigger, the actual multiplication is getting more and more expensive, right? But there's another problem here. Anybody spot it? Excellent. Very good. So even for big numbers, like near the bottom here, we're working out 25 million twice. We're working out other numbers more than twice. And this is an expensive calculation. It's 1.1 seconds. We're doing twice. Now, there are two issues here. And we're actually going to do both issues, but one demo at a time. So before I go too far here, I want to just do again another commit minus a demo 2 with timing. So we can actually, so you can see that timing information as well. Okay, so we're going to now do demo 3. Oh, something else is, if you subscribe on this link, you can get a chance to come to a course we're doing here in April that I'm doing, or get one of the Vimeo courses. I'll show this thing at the end because we don't have much time now. I will show it, don't worry. So what we can do next is we can try and parallelize the multiplication of big integer. In order to do that, I took the Java math package, I copied it into my own package. It's a separate module, so it's got the normal GNU license with class path extensions. And I'm going to use that instead of the big integer. So I'm going to do the same thing to big integer that I did to my own class. I'm also going to do the divide and conquer with fork join. So let's go to my class here. I'm going to take out the import Java math, and I'm going to instead import my own class, which is in a separate package. It's just a copy and paste from the Java 8 big integer class. And now, inside my big integer, I'm going to look for multiply tomb cook. Now that's the one I care about. I only want to do the big numbers. I don't care about the small numbers. If you parallelize small stuff, you're actually going to make things slower rather than faster. So we're going to just only care about that. And we're going to, inside the class, we're going to make a private class multiply task, which extends recursive task of big integer. And it's going to take as a parameter another one to multiply y. So it's going to be private final big integer val, and it's going to have a constructor that takes that, and then we're going to have the compute function, which is going to return, multiply our current big integer with the value. And I'm going to do the same thing for the square. I'm going to have something very similar, a square task. And the square task is going to simply say return square. Now, square is a private function inside big integer. We don't have it from the outside. And it does it automatically when you've got when you multiply an object by itself, it just uses square. It's more efficient than the normal multiply. So, these two tasks are recursive tasks. And what we're going to look for now inside this multiply to cook is any place where I'm doing multiplication. And I've got 5 different places, because what they do is they take the big number, they break it into 5 equal chunks, and they do some blah blah magic, split shifting and adding, and I don't know how it works, but we can parallelize it without understanding it, which is always useful. So you can see here I'm multiplying, and I want to send that off as a fork. And then I'm doing a separate multiply that I'm going to do with the current thread. And then I'm going to join again before I do the next multiply. So up here I'm going to say multiply task, v0 task equals new multiply task. And now we've got a problem, because the multiply task is a non-static class, and I'm inside a static context. So how do you make an inner class when you're inside a static context? Well, you can simply say a0 dot new multiply task b0. There you go. And if you've never seen that before, it's only been with us since Java 1.1, so it's quite new. Fork. And then at the end of this, we're going to say v0 equals v0 task dot join. So we join it up again, like that. We do the same thing for v1. V1 task equals da1 dot new multiply task of db1. And then at the end, once we've done the other 2 multiplies, we're going to say v1 task dot join. And we have to also fork it. v1 task dot fork. Now, I really struggled to figure out what the right place is to put this. You don't really want to fork more than one at a time, because you end up having an explosion of threads being constructed possibly, and you can run out of threads, right? We want to keep the number of threads at 8. We don't want to have more than 8 threads, because there's no point in having 2,000 threads on 8 cores. It's absolutely pointless. You're just going to waste your time. And then we do the same thing for the square tomb cook. So with the square tomb cook, we've got, again, 5 squares, 1, 2, 3, 4, 5. We're going to have a square task, v0 task equals a0 dot new square task, and then v0 task dot fork, not form. And then after I've done all the other stuff, before I do the next square, I'm going to say v0 equals v0 task dot join. Right, there we go. And then we do the same thing again for v1. Let's just copy and paste. We all love copy and pasting. And it's going to be, this time it's going to be da1 dot square. So it's going to be v1 fork. And at the end of all of this other stuff, we're going to say v1 task dot join. And if I did this correctly, which is extremely unlikely, then it should actually run faster, maybe. Have I done anything wrong? Do you see anything? V0. Okay, I'm going to go back before I run it to tomb cook. I must have. So we've got the fork. Ah, thank you very much. It helps when somebody is in the audience has actually done this before. Thanks. And this must go away. Great. Thank you very much. Brilliant. So that would have taken like 5 minutes trying to figure that one out. So, well, actually would have failed the test immediately. So let's run the Fibonacci test again. And this is now with my separate big integer class, which is, of course, not standard. It's on a different license as well. And if you run this now, this, of course, is going to be now much, much faster, right? You see our CPU is running at like 600%, 700%. So all the 4 cores are busy. They're all busy doing stuff, which is what you want. Okay, that's fantastic. And of course, it's going to be much faster because we're all working at the same time. Okay? And if you look at the output, you'll notice that it is a bit faster, but it's not as much faster as we thought it would be, right? We have improved things, but we still have the other issue that we're working out the same values several times. So that we still have to sort out. Let's write this down there before we get too excited and make this our demo 3. So we are getting faster, but not by so many factors that we're going to now go and have open the bottle of champagne. Okay. Now you can also see this, by the way, if you take, for example, like this task, the CPU history over here. So that also works very nicely. If you run this test, you'll see in the CPU history that, yeah, it's a bit small. Oh, okay, it's so busy that there's no time to do the CPU history. But you can see that we're pretty busy. Right? There's not much idle time. So that's great. But we're not getting the performance we were hoping to get. That's not happening. Okay, let's stop this and do the commit so we don't forget. Git commit A, demo 3. Bingo. And now we do the next one. The next one, we're going to cache the results. So if we don't want to work out something more than once, ideally. So we want to, if we've had it before, we want to just give that value back, not work it out over and over again. Now, one of the challenges we have is we don't want to cause a memory leak, right? Where we put it into a static field. Well, actually, you do want to, because then you can call Kirk and he'll fix your program for like 100,000 euros or something. But if you don't have that much money to burn, rather don't cause a memory leak. Don't use static collections for caching information, just randomly, because who cleans up the mess, right? No one cleans up the mess. So instead of doing that, we're going to rather just have, we're going to make a cache that's only for that run, and afterwards we're going to throw it away. Now, we might still run out of memory if we work with very large numbers, and you might still have to do something like soft references and stuff like that, which is not really ideal, but you don't want to store it inside a static field. That's the point here. So let's see how we can do this. Go back to our demo over here, and now I'm going to have a second method, one that takes a cache. It's going to be comma map of integer, comma big integer, and that's going to be my cache. Now I've got 2 methods called f, and the temptation is to leave it like that, and then it can easily accidentally call the wrong methods further down. So my trick is I rename this to something else, and then I can spot inside my IDE where I actually need to call the new f function, right? And I'm going to make this probably a private, so it's not seen from the outside. And then when I start up, I'm going to say, I'll call this f again. I'm going to say here the map from integer to big integer, cache equals new. Let's make a concurrent hash map in case it's used in multiple threads, which it is. And now we can say cache.put 0, 0 and cache.put 1, 1. And then we're going to say return f of n, cache. And of course, inside the f, we also need to change that. Now, it's very tempting to use compute absent. Don't do that. Because it will, instead of taking 10 or 15, 19 seconds, it will take eternity to complete. Right? There's a feature inside concurrent hash map that if you accidentally modify the structure of the map from inside your compute absent function, that you can end up with a live lock inside, just infinite loop inside the concurrent hash map. I was told it's a feature, not a bug. They won't fix it, in other words. this is by design. And if you read very carefully this, like the actual comment of concurrent hash map, they'll warn you about this. But anyway, I stepped into this quite nastily, and since then I know about this. So what we're going to do is we're going to not use computative absent as sexy as it is. We're going to instead, we're going to say just get and then put afterwards. So we're going to say big integer result equals cache.getIn. If result is null, which is could happen, then we need to calculate it and put it in. Here's what we'll do, is we'll do all of this other stuff. And then where we say return, we're going to say instead result equals, and the same down here, result equals. So we work out the results. And then before we exit, we put it into the map. We're going to say cache.put in comma result, and we then say return result. So now we only have to work it out once per thread. Okay, so that's, of course, much better. It should be much, much faster. Let's run it. Now you notice very quickly that we are still working out the same numbers twice. Because, well, not always, but we might get some benefit here, but not necessarily all the time. Because at the beginning of the algorithm, we often have very similar numbers. And then as we merge them together, they again have similar numbers. You see, we're going down multiple paths into this structure. We join it back together, we've got the same numbers, right? So we do benefit something. I mean, we got it down to 13 seconds. So we have improved it, but not by as much as we hoped. And so let's just put this into our code here. And this was demo 4. And let's also do our, demo 4. Okay, now, if you run this together with the task manager, you'll notice here that it's very busy, right? This is all busy, busy, busy. It's all green. So you might be tempted to say, well, we are doing work, right? So that's a good thing. All the CPUs are busy. That's great. But they're doing unnecessary work because many threads are doing the same work. So what we're going to do next is we're going to see if we can somehow optimize that. If we can, instead of doing a put and a get and then a put, we can use put if absent to put a special placeholder into the map, which can then later on be replaced with the real value. So instead of saying get, we're going to say put if absent, which is going to put in our placeholder. If the result that comes back is null, then we were the first to call put if absent, and we can start working. And if it's a special value, then we need to wait for the other thread to be finished. And if it's neither of those two, then it's a finished value, and we can just return it. Okay, so let's try that. So inside here, where we say get, we now say, instead of get, we say put if absent in comma reserved. Where reserved is going to be a field that I'm going to define, actually not as a static final, as a final field, which is going to be big integer dot value of, for example, minus 1,000. So it's a unique instance for each Fibonacci instance that I'm making. And then if the result is null, that means we won the race, right? That's a good thing. Then we can start doing the work. But if the result is equal to the reserved, then we must wait. Okay? And so the way we're going to wait here is we're going to say synchronized reserved. I'm doing my own communication here. While will become clear in a moment. Then we can say while result equals cache.getIn is equal to reserved, as long as it's still equal to reserved, we're going to say reserved.wait. And of course, you can get a interrupted exception. In that case, I'm going to here throw new cancellation exception, interrupted, like so. Okay. Now, over here, instead of just putting it in, I'm going to wrap it in a reserved synchronized block. And after I've put it in, I'm going to say reserve.notify all. So now, the first thread that manages to put the reserved in gets to do the work, and the other one's going to wait for it to finish. Now, we shouldn't see any more duplicates in our timing. Okay? You notice that? There are no more duplicates. There's only, each number only appears once. And we actually got really good time here. If you want to make it slower, there's a good way to do it. Just buy a brand new MacBook Pro, the top spec, and it'll be slower. Right? We tried that out early on, and it works amazingly well. But you can log in without typing a password. You can use a fingerprint. Okay, so this is now demo 5, and we managed to get to do it faster. And if you look at the CPU, you'll notice, I'm going to do this now quickly with top. Wait, top. Where's top? You'll notice that the CPU is not at 700% at the beginning. It's sort of, okay, it's really hard to see this. Let me show you the CPU graph, because it's a bit clearer there. At the beginning, there's a very small part where it's black, right? When we're starting up. Because there are lots of numbers we're trying to work out, and there are lots of threads waiting for the numbers. You can see it if you run it and you do a couple of thread dumps. Thread dumps tell you where this problem is. So 1 thread dump, 2 thread dumps, and 3 thread dumps. I'm going to copy and paste those into VI, which of course we all use VI, right? And we grep for worker, which are the worker threads. And you can see that in the beginning, this worker 7654321, of these, this one's you see this one's waiting, that one's waiting, and you can see that most cases they are, if it did more quickly, at the beginning you'd see quite a few threads which are actually in the waiting state, waiting for the other threads to do their work. Now, before I go on, did I do the commit? I don't think so. Huh? Let's do the commit quickly. That was demo 5. So we can solve that problem by changing the way that we block. You see, when you use a fork join pull, which is the default with the fork join, of course, you configure it with the desired parallelism. This is how many threads you want actively working at the same time. And it's by default the number of hardware threads you've got in the system minus 1. And your main thread also works, so it's basically got the whole task force there. Now, there are a whole bunch of other issues that one needs to consider with that, but we won't go into that here. So what you can do is, instead of doing a normal wait, you can use something called a managed blocker. The managed blocker allows a fork join pull to manage the way that it gets blocked. So it won't always block, it will try not to block, and if it really does have to block, it's going to start up another thread to continue keeping the parallelism high. And this is how I got that graph at the beginning of my presentation, where we actually had some really good, green at the beginning of the run. Okay, so let's try that and go to over here. So this code here, this wait and this notify, or not the notify, just the wait, is going to be encapsulated in a separate class. I'm going to put it at the bottom so it's easier to see it together with other code. It's going to be private class Fibonacci blocker implements the interface managed block. And there's only one class that actually does that in Java called the phaser in Java 7. The phaser implements managed blocker. And so when it blocks, it uses the managed blocker for that. So now we're going to, when I call it, I'm going to construct it here. I'm going to say Fibonacci blocker, blocker equals new Fibonacci blocker. I'm going to pass in the n and the cache. I'm going to pass that in. Then instead of calling blocker.block or waiting myself, I'm going to say fork join pool dot manage block with the blocker. And this actually does the interrupted exceptions. I'm going to stick it in here. This is going to go in here for the moment. And then afterwards, I'm going to say results equals blocker dot results. Okay, so the cool thing with coding like this is that I can use my IntelliJ to actually complete most of my code for me. So I can just press Alt-Enter, create constructor, int and cache, and I can say bind construct parameters to fields, and then I can say create a field for this result. Now that actually should be volatile because it's being read from a different thread to the one who's writing it, possibly. Or is it? Actually, it's not. I don't know. Let's make it volatile. It's not going to harm. And then what we need to do is this code here is going to become split between two methods which are inside the ManagedBlocker. Now, the first method that you're going to write is a method which represents your condition predicate that you've got, right? And so that is called isReleasable. So actually, the first one you're interested in is isReleasable. And it's the condition predicate, and that's basically this code over here. So we're going to say if result equals cache.get is not equal to reserved, then we can simply release. We don't have to block. And the ManagedBlocker itself takes, or the fork join pool itself, takes care of not blocking in that case. So we say not equal to reserved. And then with this block over here is going to be basically this loop that we had before. We're going to say synchronized reserved. Then we're going to say while not is releasable, I'm just reusing that code, reserved dot wait. And once I'm finished, I'm going to say return true. Okay, so I can throw away this other code that I had here, which is just for memories. And so now I no longer am going to block up the threads. The performance is not going to be brilliant in this case because it's only at the beginning that we're going to see a difference, right at the beginning. At the end, all the threads are working anyway. But if you're working with bigger numbers, it did make a difference. It depends on the context, it can make a difference. So if you look here, if you search for grep worker, you'll notice that all of a sudden I've now got a worker 14. You see? There's a worker 14. There wasn't there before. Before it was worker 1 through to 7. Now I've got a worker 7, a 14, a worker 9, but usually the total number of runnable threads is still the same. So it's basically, if you look up to here, you've got 2 threads which are waiting, or one, actually more than 2 threads. So some are waiting, some are runnable. It's a bit hard to see with this, with it being so wide here. But some are runnable, some are waiting. Whereas before, you wouldn't have had that many threads, so it picks up the slack. The actual performance for this is usually not that much better. Sometimes it even ends up being slower, just because of, stuff. It doesn't have a proper warm up, anything of that. So you have to put this into JMH if you really wanted to make this a more reliable benchmark. And that's not what we're trying to do here. We're trying to explain how the principle works of the ManagedBlocker. And with that, we actually got to the end. As I said, it's not necessarily going to be faster for this case, but for the case which I had, which was a bigger number, I think it was 1 billion or something like that, it did actually show 8% improvement because we could keep the CPUs busy at the beginning. So we've got another 1 minute for questions. And there's that link again. Oh, 5 minutes. I thought it's 45 minutes. Yeah, I'm rushing through as fast as possible. Any questions? No questions? No, he's not asking questions. That's Kirk Pepperdine. He doesn't ask questions, and he's not allowed to ask questions. Okay, Kirk, ask your question. Go on. Okay, so Kirk wants to know whether it's a reasonable idea to use parallel streams and fork join pool in a server environment. And the answer is, if you want to have a very bad weekend, then maybe you want to do that, right? Now, the funny thing is, a lot of people, when they see this, they say, hey, you know what you could do? You could actually use the completable future, and because you can do a bunch of stuff with that, and you can do some clever code with that. The challenge of the completable future is that by default, it actually constructs, if you don't specify a thread pool, it just makes one thread. If you only have one thread on, if you only have one core, like if you turn off your common fork join pool, then it just makes one thread per asynchronous task. So it doesn't actually use the common pool, it just goes, oh, you know what, we don't want to have more jobs, let's just make more threads. So this is more appropriate for, as Kirk says, batch jobs, where you're trying to number crunch a big number, you're trying to do some clever mathematical calculation. And of course, before you even look at this, you first want to see, can you perhaps get a better algorithm? Because that's going to give you many factors better performance improvement than trying to do anything in parallel. And that's always the case. It doesn't matter where you go. It's always better to say, let's try and do it, first of all, in a better algorithm. Now, so this is something which you would use when you're trying to solve a big problem with hardware, not when you're trying to do low latency or trying to have a web server with lots of different cores serving lots of people. Any other questions?
What about the quiz on slide 1?
Sorry, beg your pardon?
The quiz on slide 1, the opening page.
Oh, what about the quiz, right? What about the quiz, right? So there are many different ways you can shoot yourself in the foot with fork join. There's almost no way to instrument it. Even though I've been using this stuff for years, it did take me a bit of head scratching to put the fork join in just the right place. And if you do it wrong, it just blows up. There's no like monitoring or, as Kirk says, instrumentation available for fork join. It just blows up, or it gives bad performance. Yes? Oh, okay. You've got... Yeah, it's really hard to get anything useful from it and to actually keep it working. Now, what was your question again?
Well, I was asking about the small quiz.
The small quiz. Yes, right. So my point was, with the small quiz, which was this one over here, when you run it, you run yourself into trouble, okay? It just stops. It deadlocks because one of the threads grabs the lock by doing sysout println, and then, actually, no, that's not quite true. It tries to get the lock, but the lock is held by the main thread, and so it's not available. And if you look at this, it doesn't say deadlock at the back, but it is a deadlock, because the main thread wants the other threads to do the printing before it continues, and that thread also can't make forward progress because the lock belongs to the main thread. And what's also interesting is if you, for example, use parallel sorting, and if the threads in the common pool are not available, that just hangs up, and it doesn't work. So one needs to be careful with any of these parallel streams, fork join, especially if you're using the common pool, because they also have some special heuristics about how many additional threads they'll construct inside there. That you need to keep an eye on. Any other questions? Yes, sir. I appreciate that. That's probably the most interesting one. So that was, we were here. Okay, that is demo 6. And as I said, for this small number, it's you won't see such a big improvement, but you can see it with bigger numbers. Right, as I said, we've got this special going if you're interested. Sign up, it's time limited. I'm going to do the draw. It's a lucky draw end of this week. So thanks very much for coming and for asking some great questions.